Okay, we have here today an interesting series. We have the sum from n equals 1 to infinity of sine of n over n squared. And I kind of wish this came out to like kind of a nicer solution. I wish the answer was like pi over 4. It's not going to be quite that simple, but it's still kind of an interesting case. Now, one thing I want to do first is, I usually don't do this, but we can think about the convergence of this. It may be clear already seeing that the denominator is n squared, but what you can notice is this expression, it's kind of similar to 1 over n squared. Just noticing that for real numbers, the sign value is never going to exceed 1. It's always going to be between minus 1 and 1. And we know 1 over n squared, we know this converges by p-series. P-series just tells us that this exponent here needs to be greater than 1 for convergence, so 2 clearly meets that. What we can do to show this a little more formally is if we take this sum, we can just do the direct comparison test. So what we want on this is, assuming that we know this series converges, so then by direct comparison, I'm saying our series is always going to be less than or equal to 1 over n squared. But now one note on the direct comparison test, if we're comparing sums, we'll call this thing A. For this, in our comparison, we need this to always be greater than 0. And the trouble is sine's going to have some negative values. So what we can do actually is use absolute convergence and just put absolute value signs on this. And what you'll notice, this is always going to be true with absolute value on it. Sine is always going to be between 0 and 1. So this is going to actually be absolutely convergent. We don't have to worry about that part. So now the question is just what is the value of this thing? And that's pretty difficult just because if you look at the nature of sine, like even sine of 1, I don't really know what that is. That's going to be in the first quadrant somewhere, but then sine of 2, what's that? So it's really hard to deal with the actual values with the sine in it. But one thing I can do that is kind of interesting is for sine, I can use the complex definition. So for sine of n, I can write this as e I n minus e minus I n over 2i. And then let's just take this expression, plug it back into our sum, but then 2i is a constant, so I can bring that out front. And then because we have this minus sign, I can break this up into two sums. So let's see the first one. So for the first one, we're going to have e I, and let's write it a little bit differently. For e to the in, I'll just with exponent properties rearrange it like this. And then for the second one, same kind of thing, except now we have e minus I in the parentheses. And then what we notice is what we have here for each of these sums, these are in the form of the Dilogarithm. So our formula for the Dilogarithm is just going to be a sum from 1 to infinity of z to the n over n squared. So in our problem, the z value is just going to be e to the I and e to the minus I. So what I can do to rewrite this is we'll have 1 over 2i, and then we're going to have Dilogarithm e to the I minus Dilogarithm e minus I. And so I don't really have a nice way to simplify this. I can try to make it a little prettier and bring the 2i into the denominator. But I don't really know a better way to simplify it. I kind of wish we had some more of the properties of the logarithm. If this was natural log, or if this was just a log, then we could use the property and bring the i's out front. I mean, that would be great, but I just don't think it works that way. It's hard. I don't really know how to calculate some kind of nice value for the Dilogarithm of e to the I. If we just had I think I did the Dilogarithm of I in another video, but I'm not sure how to calculate Dilogarithm of e to the I. We can use Wolfram alpha on this and we get a solution somewhere pretty close to 1 on this. Definitely not exactly 1, but close to 1. But what I'm going to do for my final solution is just leave it like this and call it good. Maybe not very satisfying, but still pretty interesting that we can express it this way. Okay, that's it for today. Thanks everyone for watching. Have a good day.